We've seen how easy it is for Eric to assemble the new steering mechanism and validate its motion. But this only captures a fraction of the real-world behavior. To hone in on the optimal design that delivers the best rider experience, Eric will test different shapes and non-linear materials for the rubber bushing. The current design uses a simple block, but he has a couple different ideas under consideration. A B-shaped design to buckle in on itself, and another shape leveraging an elliptical cutout. To test and compare these variations, Eric will use his simulation apps on the 3D Experience platform. This way, he can start using best-in-class simulation tools right away, without the need of any manual file translation. Eric prepares the model for an efficient simulation study by removing small features like holes, pockets, and fillets without modifying the source geometry. This is simply accomplished by creating an abstraction shape, a smart associated model that Eric can modify to his heart's content. In this case, he applies two defeaturing filters, one that removes fillets with a radius of 5 millimeters and smaller, and another that removes holes with a diameter of 8 millimeters and smaller. This makes quick work of the simplification process, and additional tools are also available to remove faces of interest to simplify the model further. Best of all, if the source model changes in SOLIDWORKS, the abstraction shape and its modifications will update automatically. Continuing with the study setup, Eric leverages the powerful contact solver of Abacus by defining a general contact interaction. With this, there's no need for Eric to guess and check where components may come into contact. It's detected automatically and solved efficiently. From here, Eric defines restraints to the model: a clamp to hold the bottom in place, a hinge that allows the top to rotate, and fixed displacements for the selected translations and rotations that represent the pivot bolt. An applied rotation of 15 degrees is defined to the top with a predefined amplitude. That enables Eric to specify exactly how and when components will move. Before Eric can solve his scenario, he defines a mesh and accurately captures the geometry. Thanks to the geometry simplifications Eric made earlier, the size of the resultant mesh elements are uniform. This will reduce the time it takes to solve the study. For the plates and rubber bushing, Eric uses a swept brick mesh. Not only does it make it quick for the parts to mesh, but the brick element type is best suited for solving the high degree of deformation of the nonlinear, hyperelastic rubber material. After solving the analysis, Eric jumps right into the results and can see the excessive displacement of the rubber bushing along the axis of rotation. He toggles to the contact pressure plot to quantify his discovery, and concludes that the simple block just won't work. In similar fashion, Eric toggles to the results of the B-shaped bushing. This design shows improvement, so Eric takes a closer look by changing the transparency and visibility of components in his view. The displacement and stresses are looking better here. But what does this mean for the rider? Eric creates an XY plot to graph the reaction moment of the applied rotation to reveal how much force is required by the rider. With variations to the geometry and material, Eric can quickly compare the performance of his design ideas and move forward with the best design. The new bushing in the steering mechanism improves the rider's experience by providing the necessary level of resistance without compromising the other components in the design. By leveraging industry-leading simulation tools, Eric was able to easily reuse his CAD model, simplify the geometry, set up real-world loading conditions and materials, mesh the model with optimal mesh types, and process his results to understand how his ideas will perform without making any physical prototypes.